Hello, everyone.
See him?
As you guys know, I'm Dr. Lee Connealy, and I am so excited to be hosting our Perfectly Healthy. We have a very special, smart, brilliant person, Tyler LeBaron, who I have known for years, and I've always referred patients to his website, Molecular Hydrogen Institute, and because that is a repository for all the science that people want to know and read and hear, etc. And so, with no further ado, we have been using hydrogen water for a very long time. Right before we got on, I was talking to Tyler briefly about how we've been utilizing hydrogen water. In fact, I am reading this book that is from Japan, and it's curing cancer without surgery. And this is an 88-year-old medical doctor from China. I mean, not China, from Japan. And it's all about utilizing hydrogen water plus obviously a few other things. But hydrogen water is one of the most important aspects of his treatment. So if you're a cancer patient here, you get hydrogen regularly every day here. So you either drink it or inhale it. And so I personally drink it every day. And I have done the hydrogen inhalation. If I had a little more time, I'd probably do it regularly. But anyway, this gentleman, this doctor that I'm reading, he's 88 and he developed cancer and he did not want to do conventional treatment. So he basically recently designed his own treatment protocol, and then he is working in a clinic in Japan. So with no further ado, I want to introduce Tyler. I'm going to let him.
Says I'm unable.
There, there you
There.
are. Okay.
That
Gosh.
works.
Okay, wonderful.
That's okay. Maybe I can put this light up here if it's a little bit better. Let's see.
So I know that you did an internship in Japan, right? So
Yeah.
when did you do that?
In 2013.
Oh, great. So a long time ago, because a lot of people don't know about hydrogen water just now starting to become known.
Yeah. Yeah.
So, and I know in the
Yeah.
clinic, we've been doing it for a long time and I've known about it for quite some time. So, in Japan, what year did it start?
Primarily around 2007,
Seven.
but a little bit even before that. But 2007 we typically say is the year that it really started everything.
Okay, yeah. So anyway, meet Tyler LeBaron, guys. He is kind of the expert, right? Would you say, on hydrogen? So you tell us everything you know about hydrogen.
Well, I am very fortunate to be involved in this research. It is really fun, and I started actually back in 2009. This is when I first learned about hydrogen, and then that was what gave me the opportunity to go to Japan, to where I could actually do research as at Nagoya University and explore the molecular mechanisms of hydrogen as a therapeutic molecule, a signaling molecule, and so on. So, yeah, it's pretty exciting for me.
Yeah, that's exciting. That's wonderful because people are just now realizing. And it's interesting, one of my consults today, one of my patients who came to receive low dose chemo for colon cancer, he had colon cancer. They said he was fine. And of course, it came back. And then we did low dose chemo here with hydrogen, et cetera. And then he told me he sleeps all night with his hydrogen. So which
Huh?
a lot of
Yeah.
patients are now doing. So
Yeah.
he was
Well,
stage
I'm
4,
glad.
but he's doing great now.
Oh, oh, that's so wonderful. That's really cool.
Yeah.
Yeah.
So let's talk about how this magic works.
All right. Yeah. Should I share my screen and get into the PowerPoint? All right. Here we are. The why molecular hydrogen matters and the fail-proof way to deliver it to your cells. Okay, so I do serve as as the chief scientific officer of Inhale H2. This is kind of new for me being with commercial because for 16 years I have just been focused on research, education, and awareness of hydrogen as a medical gas, which is with Molecular Hydrogen Institute. and with his other academic affiliations, including Southern Utah University. I'm an adjunct professor there. Um, but let's talk about hydrogen. First, we want to talk about what are we talking about with hydrogen? Because hydrogen comes in different forms or species. And we're talking about this guy over here, molecular hydrogen, right? There's the two hydrogen atoms that unite together to form a molecule of hydrogen. We call that molecular hydrogen. Now, there's other forms of hydrogen that is very different than what we're talking about, such as the hydrogen anion, which is the H has the proton and two electrons, or the hydrogen cation, which is just a proton with no electron. That's the hydrogen ion, which is responsible for pH. So a lot of times we talk about the hydrogen concentration in the body, in physiology, that's referring to the hydrogen ion concentration, the H plus concentration. Totally different than the other guy, molecular hydrogen. One's an ion, positive proton, right? It's in water, the pH, the H and pH. The other one's a gas. Then, of course, there's the hydrogen atom. And the hydrogen atom is the number one on the periodic table of elements, and it reacts with pretty much anything. It can react with itself to form a molecule of hydrogen, or it can react with other things like oxygen to form hydrogen in compounds like water, right? There's H2O or methane. There's the carbon bond with a bunch of hydrogens, right? Hydrogen peroxide, ammonia, and so on, right? So when we talk about molecular hydrogen, it's important that we realize we're talking about the molecule of hydrogen that's different than the hydrogen that's already in water or that's in carbohydrates or other compounds. All right. Now, this gets exciting. This is the study in Nature Medicine, the 2007 article that we kind of mentioned a little bit that initiated a lot of the research on hydrogen gas. And this article found that hydrogen, only using 2%, suppressed the cell death of brain due to cerebral infarction. Now, you can see this picture, the 0% where no hydrogen gas was given, the white area of the brain, that's the dead area versus the 2% there's not as much white area. That's not as much dead area basically. So 2% was shown to be very effective. And they compared other concentrations. They looked at 1% that had some therapeutic effects, but not as good as 2%. And surprisingly, 2% seemed to outperform even 4%. So it's not always the case when it comes to hydrogen inhalation that a higher concentration is better. Like in this case, a 2% seemed to be more effective. So that's important. But this really is what ignited, and no pun intended, the hydrogen research. Now, there's different methods of administration, the inhalation of hydrogen, even hyperbaric hydrogen chamber. It's not so common, doesn't make a lot of sense. Hydrogen-rich saline injection is sometimes is being done, taking a hydrogen-rich water bath, or simply ingestion of hydrogen-rich water, which is very convenient and easy. Most people use it that way. So when it comes to hydrogen water, um, I just want to talk about the pharmacokinetics briefly. So here's this graph. We show on the y-axis, there's the increase in H2 concentration from the breath. Okay, we can measure breath hydrogen concentration. Because what happens is when you take the hydrogen water, those hydrogen gas molecules go into the stomach and then diffuse into the blood and then get to the heart, and the heart pumps that hydrogen-rich blood to the lungs, and you start to exhale the hydrogen gas out of the lungs. And you can see increases in breath hydrogen within just a couple of minutes, and it reaches a peak in 5, 10, 15 minutes or so, depending on the dose that you took, and then it starts going back down to baseline. So after about an hour or so, it goes back to baseline. So that's the pharmacokinetics of taking hydrogen water. And the neat thing about hydrogen, I think everyone realizes this, but just to really put a fine point on this, hydrogen is the smallest molecule in the universe. And that allows it to penetrate the cell membrane, the blood-brain barrier, it gets into the organelles, the mitochondria, very easy, easier than anything else, because these other like drugs and supplements, they have to go through different transporters because maybe they're large or they're charged or they're polar or so on. So they have to go through these protein channels, and it's difficult. They can get saturated, or maybe the kinetics is slow, or and so on. Versus hydrogen, it can just diffuse right through the cell membrane and reach these subcellular organelles. And so it's really great for treating things of the brain or a whole bunch of different areas because it can really get right to the area that needs it the most, such as, say, the mitochondria. Now, there's a couple fascinating things to talk about this. A lot of us have heard of alkaline ionized water or electrolyte reduced water. Now, this is actually a source of hydrogen, but they didn't know it back then. The research on ionized water started way back in the 1930s, and in 1965, it was approved by the Japanese Ministry of Health, Labor, and Welfare. And in 1985, there was a lot of testimonials, and that really started a lot of the hydrogen research, sorry, a lot of the research on alkaline ionized water. But again, nobody really knew why it was giving any benefit at all. And that's the question, right? Well, is it the pH? But most of your medical professionals and scientists are like, well, this doesn't make sense because water is not a buffer. I mean, just a little bit of lemon juice, it gets neutralized immediately. The body already regulates the pH. Maybe it's like the water structure or something, but that's been largely debunked by so many chemistry studies that that the water structure itself has not changed. So what's going on? And when you think about it, when you do electrolysis of water, the definition is literally the decomposition of the water molecule to oxygen gas and hydrogen gas. So you can see in this electrolysis diagram, hydrogen gas is being produced. So maybe hydrogen gas is a therapeutic agent of alkaline ionized water. And it turns out it is. And we published this article a couple years ago, but I would suggest anybody who has any interest in looking at this deeper to really check this article out because it is a comprehensive review of numerous publications on alkaline ionized water that conclusively demonstrate over and over and over again that when you remove hydrogen gas from alkaline ionized water, all the benefits are gone. And that's why a lot of people, when they use these types of machines as well, sometimes they get benefits initially, but that doesn't last. And that's because hydrogen gas is not super, doesn't always get produced in the water or stay dissolved. So a lot of things about this. So it's a very fascinating article for those who are interested in looking at this more and some caveats with that as well. And then, of course, so it's hydrogen water. Now there's inhalation. Now we're going to really focus on this because there's a lot of confusion and misconceptions about that, and it's very interesting. And I'm going to present to you largely a presentation that I gave in Japan just a couple weeks ago to all the academic researchers, and it was really exciting because a lot of other researchers were coming to the same conclusion that I was, and we are writing a paper right now that we hope to get published soon that really helps to standardize hydrogen inhalation therapy of how we can monitor the dose, concentration, and therapy, and how to think about it and everything. So you're some of the first people besides the researchers in Japan. Actually, it was an international conference, so there's over 20 countries that came. But you'll be some of the first people to see some of this stuff and what we're thinking about when it comes to hydrogen inhalation. So first, just some background on hydrogen inhalation. Like, why does it even matter? What are the benefits? Well, that 2007 study we talked about, that on the cerebral infarction, a stroke model, well, that was really powerful in animals. So the question is there benefits in humans? And 10 years later, this was in 2017, this study looked at the hydrogen gas inhalation as a treatment for cerebral infarction. And they took 50 subjects and randomized them to a hydrogen group and a control group. And here are the results. Basically, they found that in the changes in the rating scores and in the MRI signal intensity, that hydrogen tended to outperform the standard treatment group. So its control was not just placebo. Actually, it was a standard control group with standard therapy. So it actually outperformed what people would normally do. So this is very encouraging, right? So hydrogen really good for the brain, just like that rat study showed in Nature Medicine. So it's pretty cool the fact that this research can be translated from animals to humans as well. Another big one is post-cardiac arrest syndrome. And when people are going in for a surgery or you have a heart attack and then you have to resuscitate the heart, well, what happens is that oxygen-rich, nutrient-rich blood goes back to the rest of the organs, and you get this reperfusion injury, and it causes a lot of oxidative distress and a lot of problems. And so even once the person gets resuscitated, their survival isn't very good. And so, like in this study, in these this in these rodents, the survival rate, as you can see in this graph, went down to 43%. After 24 hours, only 43% survived. And then you compare that to TH, which is therapeutic hypothermia. That's the standard treatment, and it went up to 77%. So that's basically targeted temperature management, and that's pretty much what's done right now in these types of situations. They monitor that temperature, maybe bring the temperature down a little bit because it helps slow down metabolism, reduces the amount of oxidative stress that's occurring, and so on. But then when they tried hydrogen gas, that survival went all the way up to 92%. And then when you do the combination, there was 100% survival. So it's a really powerful animal study. And that gave a lot of credence to the idea that we should do this study in humans. And with that and some preliminary data, the Japanese government approved for the use of hydrogen inhalation for post-cardiac arrest syndrome for these patients, so they could do a major clinical study in the hospital setting. And that's exactly what happened, is published in eClinical Medicine, part of the Lancet, the efficacy of inhaled hydrogen on neurological outcomes following the post-cardiac arrest syndrome. And this is some of the data. So the multi-center RTC across 15 hospitals in Japan. So comatose patients, there were 73. Now, there was actually going to be a lot more, but this is during COVID, and so there are a lot of issues with trying to do recruitment and everything. But 73 is how many they were able to get. Following out of hospital cardiac arrest of cardiogenic origin, and then they use standard care with or versus without 2% hydrogen inhalation. And then 3 month, this is the results. So 3 month survival rate in 85% versus 61%, favoring H2. So it was a 39% improvement for the 3 months. So think about that, right? A 39% improvement for the 3 month survival rate by inhaling 2% hydrogen gas. The neurological recovery, there was a 46% versus 21%, again favoring H2. So nearly double the rate of full neurological recovery. So pretty impressive results with this pretty impressive study as well. And again, showing that some of these animal data can be translated into human studies. They use 2% hydrogen gas. And they did this, a lot of these studies are done with, like, say, a tank of hydrogen gas, a tank of pre-mixed gas, right? Like when I was doing my PhD, we used a tank of mixed gas, and 21% oxygen, 2 or 3% hydrogen gas, and then the balance would be nitrogen. And that's what we would use. And the same thing with these types of studies. They put it like right into the ventilator. That way, every inhalation they take would be exactly that percent of hydrogen gas. It's not just nasal cannulas and everything, because how do you really know you're getting 2% with every single patient in all the cases? And again, as we saw, the 2% could be more effective. So just to keep that in mind as we go through this presentation. And that's why we have to use this term, the fraction of inspired gas. In medicine and respiratory physiology, the term fraction of inspired gas was introduced 75 years ago to quantify the fraction of a gas that is actually inspired during inhalation. Like in oxygen therapy, we say FiO2. And that's true with all gases, like fraction of inspired carbon dioxide, FiCO2, FiN2O, and so on. So for hydrogen, the fraction of inspired hydrogen, FiH2. That is the terminology that we should use when we are talking about using hydrogen in studies, in patients, looking for different products or devices. It's all about the FiH2, not the flow rate, because the flow rate doesn't tell you anything. You want to know the fraction of hydrogen that's actually being inspired. And the flow rate doesn't tell you all that, as we're going to get into. As we define the fraction of inspired hydrogen, it's basically the volume of inspired H2 gas over the total volume of inspired air. It's pretty much just like that. And why is that so important also? Because FiH2 via Dalton's law can be related to partial pressure. Why do we need to know the partial pressure of hydrogen gas? Because the partial pressure, according to Henry's law, is going to equal the cellular hydrogen concentration. Why is that important? Because the cellular hydrogen concentration is what determines whether or not it's going to be therapeutic, right? You have to reach a therapeutic threshold in order for hydrogen gas to be effective. And therefore, you need to make sure you have a partial pressure that's high enough to get to the therapeutic effect. Therefore, you have to make sure that FiH2 is at the desired
Mm.
targeted percent in order to get these benefits, to get that therapeutic concentration. So that's the logic. That's why it's very important to monitor the FiH2. The question then is, what is the optimal FiH2? Well, when we look at this in vitro, like cell culture data, it's actually all over the place. And it's too paradoxical. It's not really relevant. There's a lot of caveats to that, so we can't really do it. Also, it's difficult because no clinical studies directly compare different values of FiH2. So what we have to go off of is what do clinical studies currently use and so the animal studies. And several in vivo animal studies did compare different FiH2 values, and a number of them indicate that 2% is more effective than 4%, such as the people we looked at and some other articles as well. The fact is, most clinical and animal studies use a concentration that will deliver effectively between a 1 to 4% FiH2. So here's a pop quiz for you. Why ensure a precise FiH2 about 2 to 4%? Let's mark all that apply. Because A, it ensure targeted cellular H2 concentration. Is that important? Do we want to make sure we get the right cellular concentration of hydrogen? Yes. So let's mark that one, yes. Because it's not flammable. Yeah, because if it's be less than 4%, it won't be flammable. If it's higher than 4%, it is literally explosive. That's hydrogen gas, right? So that one, yes, check. How about allows for comparisons? Well, yeah, that would make sense because if we can have a precise hydrogen, like 1, 2, or 3, or 4, or whatever percent, we can literally compare the different concentrations. That makes sense. It also reproducibility among studies and clinicians. Yeah, that way, you have one patient and they're, a sumo wrestler, and this person is a child or an elderly grandma. You don't know what the FiH2 is based upon flow rate. Like, how do you know? Unless you know what they're actually getting, what they're actually inhaling, what the FiH2 is. So it's very important, as well as for mechanistic elucidations, because again, we can know what the concentration of hydrogen is and we can understand the mechanism. And also, if it's true that 2% is more effective than 4%, like some of the animal research suggests, then that's going to be important because we want to target that precise FiH2. And again, if a certain percent is more effective than a different percent, we must be able to control for the targeted FiH2. So there's other reasons, but these are very important reasons why we need to know this. So here's the part we have to understand. In the studies, the delivered H2 is the same as the FiH2 because like in a petri dish, we will literally incubate the cells in an environment containing say 2 to 4% hydrogen. Or an animal study, we literally connect, see these tanks of gas, oxygen, nitrogen, hydrogen, we literally connect those tubes to the animal cage and make the entire environment 2 to 4%. So the animals running around, on their wheel or whatever, they're inhaling 2 to 4%. You can imagine the human, the same idea. If you can make a contraption and they're inside a chamber that's exactly 2 to 4%, it doesn't matter, who else is on the chamber or how they're breathing, whatever. The delivered hydrogen concentration is the same as the FiH2. And the clinical studies, they use a mask and they deliver precise concentration of hydrogen with tanks in order to give it a 2 to 4% hydrogen concentration. That's how it's done. So here, H2 concentration that's delivered is the same as the FiH2, what's actually inspired. However, with nasal cannulas, the delivered H2% is not the same as the inspired H2 fraction. So you have these different machines in the market that maybe they produce 2 to 4% hydrogen with a nasal cannula. So what's being delivered is 2 to 4%. Or you have these oxyhydrogen type machines that deliver 66% hydrogen, or other machines that deliver 100% pure hydrogen. Well, just because it delivers 2 to 4 or 66 or 100% does not mean that that is the fraction that you actually get. The fraction depends on many factors. What is the flow rate? Right? If you can imagine, if you have a machine that gives, say, 100% hydrogen gas, but the flow rate is only, 10 milliliters per minute, then you're not going to get any hydrogen in your body, right? So the flow rate really matters. And then, of course, what's the H2 concentration, your minute ventilation, your respiration rate, the inspiratory flow, the K or waveform factor, entrainment, duty cycle, inspiratory exchange ratio, reservoir effect, geometry and prong fit, nasal patency, mouth versus nasal breathing. All of these factors are going to determine what the FiH2 is. And we're going to talk about some of these so you can get an idea of what flow rates or things you need to consider to target the desired FiH2. And it's just this equation right here. There it is. It took a long time to put these together, but I'm very excited about them. So there will be a quiz at the end on these equations. But we're gonna break them down for you though a little bit. Just what the meaningful part. Really just want to focus on this right here. So the FiH2 is the equal to eta QH2 over MIF. So the QH2, what is that? That's just the cannula H2 flow rate, right? So it's not the total flow, it's the H2 flow. Because again, if you have oxyhydrogen, it's only 66% of the total flow. So you want to know what the H2 flow rate is, and then you're going to divide that by the MIF. What is MIF? Well, MIF is the mean inspiratory flow. Now, if you think about this, H2 only enters the lungs during the inspiratory time, which is only about 1/3 of each breath, so about 20 seconds, right? We're not inhaling the entire time. Like we actually exhale, and our exhales are normally longer than our inhales, and we have a transition period, right? So the way this is calculated is the MIF would be equal to the minute ventilation, right? Whatever that is, of how many time, the amount of air you are moving per minute. That's the minute ventilation, divided by the total time spent inhaling, like so seconds per minute, and that's going to give you your MIF. Or if you just simply VE, minute ventilation, divided by DC, which is the duty cycle. And the duty cycle is exactly that, where it's the time spent inhaling divided by the total inspiratory time. Okay, so pop quiz for you all. We love these quizzes, right? Resting minute ventilation is 5 to 8 liters per minute. True or false? Well, the answer is true. That's true. That's standard textbook. We know that. However, that's true in a supine, fully relaxed position. That's not true for practical rest. When you're seated, you're mentally alert, you're engaged. Let's say you're at a clinic and you're inhaling hydrogen, or you're at home and there's hustle and bustle going on. You're watching a show where you're working or you're doing gesturing. All of a sudden, that minute ventilation goes up tremendously. And that's important if we're trying to target the concentration of hydrogen, the FiH2, that we actually want. So in this graph, you can see how mild things like quiet sitting rest, seated work, speaking, gesturing, this increases the minute ventilation quite dramatically. And this is just for somebody who weighs 70 kilograms, 150 pounds or so. Uh, and so minute ventilation, the practical minute ventilation we actually have to use ends up being quite higher. So we can do this a little calculation here. And again, this is important because we want to target the FiH2. So this mean inspiratory flow, we can take the minute ventilation, and it could be anywhere from less to 6 to even up to 16. And let's just take an average. Let's say 10 or 12. Okay, that's where we're at right here, 10 or 12. And then we divide that by the seconds spent inhaling. And typically it's 1/3 of the time that we're inhaling. So 10 or 20 or 24 seconds. So 10 divided by 20 or 12 divided by 24, right? Or if you're using DC, that duty cycle, 0.4 or 0.33. Either way, you get the practical MIF values, which averages 30 liters per minute or 500 milliliters per second. And the range is pretty large. But we want to keep these numbers in mind. The average MIF, mean inspiratory flow, is about 30 liters per minute or 500 milliliters per second. So, and as I put here, MIF is roughly 2.5 to 3 times the minute ventilation, but it can be a little bit less or a lot more, over 12 times more. So this is, breathing. A lot of people breathe differently. Like maybe they're doing specific type of breath work. Maybe they're meditating. All of this is going to change the DC, the duty cycle, and therefore it's going to change the total time spent inhaling, right? I mean, you could potentially, if you wanted to, you could inhale really slow right, for a full 45 seconds, then exhale, right? That would be really hard to do, but you could do that. In contrast, a lot of breath work type stuff, you are taking a faster inhale and then a really slow, long exhale, right? And this breath work, it directly changes, this is changing the inspiratory exchange ratio, directly changes the duty cycle. And in turn, that's going to change your MIF, right? Your mean inspiratory flow significantly, right? All the way up to maybe 90, for example. So this is why breathing style, how the individual, how your patient breathes, are they anxious? Are they doing meditation breathing? Are they kind of alert? How are they breathing? That really, really changes the mean inspiratory flow, which is going to directly influence the fraction of inspired hydrogen. So we like to use 30 liters per minute because we went through that math and it works out pretty good. In fact, all of these, if you change different inspiratory exchange ratios with different DCs or different minute ventilations, right, up to 15 liters per minute, all the way down to 4, all of these combinations give you a 30 liter per minute mean inspiratory flow. So it's really is a good number just to, for simple basic math, thinking, okay, around 30 liters per minute. So basically, as a rule of thumb, right? You have textbook rest. If you're really resting laying down, yeah, maybe your mean inspiratory flow is on around 20 liters per minute. But again, 30 liters per minute is where you want to be. And the range, though, could be, and this is again important, it could be even less than 10, but it could be potentially even over 100. That mean inspiratory flow, we've spent a lot of time on this just because it forms the foundation, the base, literally, it is a denominator of that equation of how you calculate your fraction of inspired hydrogen. But we mainly can just use 30 liters per minute. And there's some limitations though, because that doesn't tell the whole story. Because mean inspiratory flow is literally the mean, it's the average, and that indicates like a rectangular breathing. Like we don't like when we inhale, we don't breathe at a very specific flow and then just like stop and then we exhale and then like it's not just this rectangular thing. There's a triangular pattern to this, and this is kind of represented here. We start breathing, our the very first phase of our inhalation is fastest. We have the very fastest inhalation, and then it goes up and it slows down. So as you can see, it peaks, and then we're still inspiring, and then it goes down. So at the very end of the inspiration, there's that little transition. That's when you start to slow down. Well, what do you think is happening during that portion of inhaling with the hydrogen gas? What's happening to the concentration when you are inspiring really fast, right? Versus at the very end where it's like you're barely inspiring anything at all, and you're just about to transition, right? That changes things dramatically. And those things need to be taken into consideration under certain conditions as well. Okay, now we get to eta, the capture efficiency. This is the other big part of this equation before we can get into the other important parts. The capture efficiency is essentially the fraction of delivered gas captured during inspiration. And this equation is the volume of the cannula gas that is inspired over the volume of the cannula gas generated during inspiration. Because if you think about it, um, maybe the prong's not on all the way, the nasal cannula, for example. Or maybe you're doing mouth breathing, right? And you're not breathing through your nose at all. You're only breathing through your mouth. Then you're going to get very little, a small portion of that hydrogen gas into your body. So that eta is very important. And yeah, it can be up to 1 if everything is perfect, like coached, really well put in cannula, and it's basically nose in and then exhalation out, right? If you're doing all of that, then it's going to be a lot higher. The estimation, again, like I said, assumes a closed mouth, nasal breathing with a well-seated cannula. And there's contributors that's going to reduce this. Habitual mouth breathing. How many of us have a patients or ourselves that breathe often through our mouth instead of our nose? Maybe turbinate hypertrophy, rhinitis, congestion. Yeah, maybe you're sick, and so you're not breathing very well through your nose, and you're sick, so you want to use hydrogen, and you're not getting very much because you have a congested nose. maybe prior trauma, septal deviation. Estimated population that may have an ADA of less than zero point 0.6 could be, 10 to 15% of general adults and maybe 20, 25% of adults over 65 years. So it's a pretty big factor we have to consider with everybody. And then there's this part, which is the reservoir effect. Um, we don't need to get into all of that, but it's another potential boost to the hydrogen concentration because you do have a reservoir in your nose. So now putting this together and calculating these things out, we can make this graph in order to figure out, okay, what is the minimum required H2 flow rates to reach 1% FiH2? Because as I mentioned in the studies, we want to hit at least a 1% FiH2 to be therapeutic, but ideally maybe 2%, maybe not higher than that. And this graph basically has on the y-axis is the required flow rate in milliliters per minute from 0 to 700 milliliters per minute, and on the x-axis is the mean inspiratory flow. And then we have the graph basically plotting a pessimistic, a typical, or a lower optimistic portion depending on what your eta is, how much hydrogen you're actually capturing. But it's all centered around this 30 liter per minute. And as you can see, you're going to be probably around 200 to 300 milliliters per minute is a minimum that you would need for the typical adult in order to get at least a 1% FiH2. But there are occasions where you might need a flow rate well over 600 milliliters per minute in order to get that 1%. Whereas for a different patient, you might get away with, less than 200 milliliters per minute. So if you give us a patient let's say have several patients, or maybe have more than that if you're a good doctor. You could, if you give them all the exact same machine, some patients are getting way above 1%, and other ones are not even getting 1%. And so it makes it really difficult. And that's why things have to be tailored to every individual. You want to we know what the targeted FiH2 is and make sure that they're getting the right flow rate. And so here's a table I put together with all these calculations, and we can calculate for 1, 2, or 4% based upon who we want to target, right? There's going to be at a lower bound, maybe as low as 60 milliliters per minute. You're gonna be able to get a hydrogen for 1% for some people, but most people not. You can target 68%. This is kind of like the standard deviation idea. If you want to target 68%, you probably want to get at least 318 milliliters per minute. This is like these are recommendations for the minimum flow rates, but we tend to think it's closer to 2 to even 4% is better. So that puts you up to 650, maybe up to 1500 milliliters per minute. But again, you're going to have some patients that because of their build, their nasal patency, and their respiratory profile, and all of these things, they need a much higher flow rate, right? I mean, look at these numbers, right? This is 3,100 milliliters per minute, and potentially even over 5 liters per minute, which is, insane. And that of course going to be very flammable and dangerous as well. So there's just really illustrating that every individual is different, and you have to target flow rates to get the targeted FiH2 so that you can make sure you're within the desired range. So now some maximal recommended flow rates based upon hypoxia and flammability, because this is often a concern. Well, people are concerned, well, what if I get hypoxia? And that's why they want to use oxyhydrogen. But then, of course, there's the flammability aspect with hydrogen in general, because above 4%, it is flammable. So when it comes to hypoxia, it's actually not a big concern at all, because the atmospheric air is already 21%. And high elevation, like in Bolivia, that's a lower pressure, and that's equivalent to an FiO2 of about 13.4%. And the people in Bolivia, they thrive. They're just fine. There's no problem. Now, there's actually, of course, if you're too high, like in the up like Mount Everest or something, I mean, yeah, you're not going to thrive. People that are really high elevation, it's not good. But in general, people who at our mild elevation, like Colorado and some other areas, where the partial pressure is reduced to around 15%, 18%, they tend to have better in terms of mortality and different diseases and different things. So you having a slightly lower partial pressure of oxygen is actually correlated with a lot of benefits. You don't want too much oxygen all the time. because you don't need it. So, and hypoxia typically occurs between a 10 to 15% FiO2, depending on lung function. And again, we can go down as low as 10% as long as you have healthy lung function. You're just resting. So an FiO, so a 15% FiO2, to get that, you would require an FiH2 of 30%. So that's a very high and flammable concentration. So for an average person, that would require an H2 flow rate of over 10 liters per minute. So hypoxia really isn't a concern for most people. But because hypoxia is a very problematic if it does happen. You have to consider who is the patient, like children, elderly, somebody with a really high ADA. In these cases, it's possible that even less than 2 liters per minute, if it's like a small child, for example, and they're just inhaling pure hydrogen gas, yeah, they could potentially get hypoxia. So again, you really have to know the patients. You can't just say, the same flow rate for everybody. Now, flammability guidelines. In air, H2 gas is flammable above 4% and below a 75% concentration. And the risk of flammability and detonation becomes virtually inevitable above a 10% if an ignition source is present. So to completely avoid any risk, really the FiH2 should be less than 4%. Essential to be less than 10%. And this is important because there are a number of documented cases in the literature where people have been inhaling hydrogen gas with a nasal cannula and they've had an accident, an ignition source,
Mm.
and they've had facial fractures, they've had internal bleeding, they've had explosions inside their lungs, they've had to be rushed to the ICU. These are documented cases just in Japan to the Japanese Consumer Affairs reports, and there's articles about this published. The
Mm.
amount of energy required to ignite hydrogen gas is less than the amount of energy required for static discharge. So you don't even walk across the carpet and you touch your doorknob. That's just static electricity. It has to require a certain amount of energy to make that jump. It requires less energy to ignite hydrogen gas than it does to have a spark. And and if you think about the scary stories with these hyperbaric oxygen chambers, where just somebody moves the blanket and there's a little static, right? And then there's a major explosion. Well, remember, oxygen itself is actually not flammable. Oxygen is just an oxidizer. And yet, static electricity could have that effect. And that's why there are so many laws and regulations, and you should be trained. There's so many things to consider with hyperbaric oxygen chambers because they can be a really great tool when used appropriately. But these are real risks. Well, hydrogen gas is a fuel, and the ignition to light hydrogen gas is very small. And but often people they don't really feel concerned about it because they've been using it all the time and they put it close to a candle or something and nothing's happened, so therefore it's okay. It's kind of like, well, my uncle smoked cigarettes, until he was 98 and he's still fine, so therefore cigarettes are not bad for you. um, we have to be really careful, especially if we have patients and they're going to be doing this at home, or if it's in our clinic, we think about insurance wise and all these things. So just the there are grave concerns and things have happened and it has been reported. Korea, Japan, and China, and here in the US, and other people that I've heard about. We just have to be very careful about these types of things. And especially when using oxygen, like oxyhydrogen, because as we talked about, there's no additional benefit to using oxygen, but it does dramatically increase the risk of explosion because any combination of hydrogen and oxygen is going to be flammable versus hydrogen in air is only flammable above a 4% concentration. So very important. In fact, I do talk about this here. Some of those these are some of the reports reported in the literature. Vomiting of blood, explosions, facial fractures, contusion of the lungs, and so on. So just
Yeah,
really got to be
right.
careful about this stuff. Okay, so since H2 is not flammable but above a 75%, this may give a false sense of safety when using 99% H2 with a nasal cannula. Because you're like, well, it's 99%, it's pure H2, it's not flammable. But remember, as soon as the pure H2 leaves the cannula, it immediately gets diluted below 75%, making it flammable. Even a flow rate that is too low to reach a 1% FiH2, because the person is breathing quickly, they have a high mean inspiratory flow, but during that time, like say the end phase of inspiration, it can transiently become flammable as the H2 gas fills the nasal passages. during the transition and exhalation phase. So you got to be cautious about that. In fact, based upon our practical resting model of 30 liters per minute, although H2 flow rates of less than 200 milliliters per minute can feasibly create flammable pockets, the increase, the risk increases significantly above 600 milliliters per minute. And the flow rates that exceed 1600 milliliters per minute are certain to exceed flammability limits and may become detonatable. So lower values of MIF and respiratory flow increases flammability risk. So look at this table just to kind of really put a fine point on this. When the one column, they have a lower flammability risk. So an adult using this. Compare that, a child using the exact same flow rate. For the child, all of a sudden it's a high flammability risk because at MIF, the mean respiratory flow is totally different. There's things that are so different. So adult, maybe they're fine, no explosion, no hazard. But for the child, it is. Or during the day when you're practical resting, right, your mean respiratory flow is higher versus the nighttime, you're going to sleep with the machine. Now it becomes potentially flammable. Practical use of mild activity or meditative. A husband uses it, right? That maybe the larger. I guess we could have switched it, but in general, husband use, wife use, smaller, mid-age grandpa use. These are just some examples. Just saying this is some of the problems with just saying, oh yeah, this is the flow, and then everything is just fine. That's not necessarily the case. So hypoxia potentially, depending on the individual, less than 2 liters per minute, but most likely everyone's going to be fine. Even have to be higher than 10 liters per minute, so it's really not a concern. Flammability, well, even less than 200 milliliters per minute. I mean, you can literally capture hydrogen gas and then you could fill up a plastic bag and ignite it, and it's a little bomb. We do this in chemistry lab experiments and different times for demonstrating the flammability of hydrogen gas. But you hit these different areas. Once you go above 600, you start getting more into a red zone, and then above 1.2 liters, you're really starting to put things at a much greater risk. So these guidelines, of course, as I mentioned, do not apply to oxyhydrogen because it is flammable. Oxyhydrogen is flammable and detonatable at any flow rate and does not carry the risk of hypoxia at the high flow rates. And just another brief comment, those with healthy lungs do not benefit from an increased FiO2. As long as the FiO2 is above 50% and the SpO2 remains above 94%, it's fine. So if SpO2 is 90% or higher, then O2 if SpO2 is less than 90%, that's when you use supplemental O2, which is typically at 1 to 6 liters per minute, right? It's a lot more than what you're given with oxyhydrogen. And also, there's no evidence supporting claims unique to HHO or Brown's gas, such as altered molecular structure, electron, plasma effects, and there's a lot of things out there. There's no evidence, but there's a lot of evidence actually that debunks those claims. A high flow oxyhydrogen may modestly benefit individuals with mild lung impairment. Yeah, if you need oxygen, then it's possible, but there's the risk. Also, excessive oxygen delivery for a prolonged period in healthy individuals may induce hyperoxemia, which could be bad, oxidative stress. At same H2 flow, oxyhydrogen is not more therapeutic than pure H2. That's very true. They've been demonstrated in studies. Oxyhydrogen poses greater flammability hazards than pure H2, requiring strict safety precautions in both clinical and home use. So some very brief guidelines, because there's so many caveats I went through, but kind of distill it all down. Minimum threshold, you do want to get at least 1%, or else you're probably going to be subtherapeutic. For typical adults, that means a flow rate of at least 200 to 300 milliliters per minute is where you want to be. Optimally, you want to be 2 to 4%. That's where the studies are at. That means you want to flow it between 500 to 1500 milliliters per minute, depending on the individual, right? And again, if you really depend on the individual, it's going to be a lot wider than that. And then your maximal flammability. You don't want an FiH2, it needs to be below 10%, but ideally not above 4%. That means the flow rate, again, typical adults should not exceed 600 to 2000 milliliters per minute, which is problematic. And then, of course, maximal hypoxia, you don't want to exceed 30%, which is already way higher than the flammability level. So basic recommendations, if nasal cannula is the only option, then the flow rate should be tailored to the individual. You need to, step one, right? Determine the target FiH2. Are you trying to do a 2% or a 4%? Because depending on the condition, one could be more effective than the other. Then you estimate the required H2 flow rate via estimating the mean inspiratory flow. What is a minute ventilation? The body size, the VO2. There's ways to calculate what that probably is, or if you can't measure it, what is their inspiratory exchange ratio? Like how are they breathing? So you can again calculate the mean inspiratory flow. You estimate the capture efficiency. Are they doing nose in, mouth out, and figure out what that nasal patency is, and so on. So and for the researchers, of course, when nasal canyons are used, it's important to estimate the FiH2 in the study. So in summary with this presentation, this part of the presentation, the FiH2 is important because that's going to dictate the partial pressure, and that's going to dictate the concentration of hydrogen gas in the cells, and that's going to determine the therapeutic effect. And FiH2 between 1 to 4% is ideal. You don't want to go above 4% unless the evidence clearly warrants it because of the increased flammability risk. The precise 1 to 4% FiH2 unfortunately cannot be delivered via nasal cannula because your breathing is all over the place, right? Sometimes it's 1%, sometimes it's 4% or higher, it's all over. Depending on MIF and DC, the required flow rate ranges between 300 to over 1500 milliliters per minute. Ranges, 60 to over 5,000. The range is huge. Flammability, avoid flow rates more than 600 milliliters per minute, especially those above 1500 milliliters per minute. In general, use an MIF of 20 to 40, we say 30, to estimate FiH2. Okay, so that's going to be that's the kind of summary of some of that math behind this. And then so just spend a few more minutes. And first, I want to share some really cool thing. You're some of the first audience to hear about a groundbreaking discovery about hydrogen, about the mechanism of hydrogen, about how it actually works. Here it is. I just posted this to social media. If you're not following H2MHI or me on social media, you probably want to do that. But we just published this article after 10 years of work, and we found that the risc-gate iron sulfur protein is a primary target of molecular hydrogen. So that's a protein inside the mitochondria that hydrogen seems to selectively target. It modifies, it gets degraded, and that causes a little stress in the mitochondria, which causes the mitochondria to induce this mitochondrial unfolded protein response, which that ends up resulting in the rejuvenation and regeneration of the mitochondria and provides a whole bunch of therapeutic benefits. You can explain so many effects of hydrogen with this mechanism. So for the first time, we actually have a precise target and mechanism of how hydrogen is really working. So it's very, very exciting. Now, with the MHI, our purpose, of course, is education. We do have courses available for people if you're interested in taking courses to learn more about some of the basics of hydrogen. We've had kids take them, like elementary kids, but also a lot of PhDs and researchers and medical doctors. They really love them. It really gives a good foundation. And this is all there. So we invite you to look at those, or even join our MHI community because we answer people's questions all the time. And there's a lot you can do to help us spread the research awareness of molecular hydrogen. And I'm very excited about hydrogen, and so I've been saying this. Hydrogen is coming. Many of you, like Dr. Connealy was saying, she knows hydrogen's been around for a long time, but it's just growing. It's getting bigger and bigger. And I think that in 2027, there'll be another inflection point, but by 2037, hydrogen will be widely recognized as a therapeutic gas. That's my prediction based upon the clinical studies that are going on. So I'm really excited to do that. And of course, we need more research on hydrogen, though, for this to happen. We need to understand the mechanisms, the dosing protocols, method of administration, and so on. And so again, I want to invite you to come to Molecular Hydrogen Institute, get certified, join the hydrogen family, and so on. And now I want to spend just 5 minutes to just briefly introduce this machine. That was my MHI presentation, and what I'm about to present now is completely independent of MHI. So you don't send an email or something to MHI for this or things. I think Dr. Connealy will have some links available for this, but I want to explain this machine briefly because the entire presentation I just gave is precisely why I helped to develop this machine. Because when I was doing my PhD research, as I mentioned, we had to use tanks and premixed gas and doing all these things to ensure the precise concentration of hydrogen and the FiH2 and everything we needed to do. There was no machine we could use for animal or clinical research in the way we wanted to. And this is exactly what this does because, as I said, nasal cannulas, it doesn't, the flow rate does not equal the FiH2. It doesn't, we don't care what the flow rate is. We care what the FiH2 is. That's what matters. And so just as I showed this example, right, you can see this bag of 2 to 4%. That's what our machine has inside. In fact, you could literally put our machine right there, and that's how our machine works. There's a bag inside, an inflatable bag using a non-rebreathing mask that ensures that every inhalation you take comes from inside that machine. So you know that in this case, the delivery of hydrogen is the same as the FiH2. As it says, ensures every inhalation has a therapeutic FiH2, ensures a precise FiH2. You can adjust it between 1, 2, 3, or 4%, and there's no risk of flammability since H2 doesn't exceed the lower flammability level. With that, thank you for your attention. That was fun. There we are. There it is.
Yeah, it's fabulous. So a couple of questions. I mean, here we use it for every medical condition. There's not a medical condition that molecular hydrogen for either prevention, optimization, or any disease, whether it's neurological, cancer, or anything. And I know one of the questions was, can molecular hydrogen help with long COVID?
Yeah, it's a great question. And actually, some of the data would suggest that yes, there are some. This is an interesting one. There's a number of studies, both in animal studies, that would show that because when we look at the mechanisms of what's going on with like your cytokine storm, for example, all
Right.
the inflammatory response, your dysregulation of oxidative
Mhm.
stress and everything, and what we just talked about with hydrogen improving the mitochondria, those directly get to the root of what's going on with long COVID. And there are some studies that have been done with COVID, and there's some that are ongoing right now. Some of the first studies, and it wasn't long COVID, but just COVID in general, really showed that hydrogen could play a tremendous role in benefiting the subjects. So I think more research needs to be done so we can have the clinical data on that. But there's some preliminary data already, and then with COVID in general, that does already exist.
Right. So, as you know, people have used not only inhalation but tablets. And so this patient said, we also have the hydrogen water machine. But the question is, how do you measure hydrogen content in water to determine its level?
Yeah, it's a little bit challenging because hydrogen is a small molecule. You can't just like get a normal meter and measure it. So we in the lab we typically use gas chromatography, and that's the gold standard way. For the normal
Mhm.
consumer, it's challenging. The best way is to use like the methylene blue or H2 blue, for example. You can get on Amazon, and if you, it's more of an art than a science, but you can it's a titration reagent basically, and so the methylene blue literally consumes the hydrogen molecules, and then you're able to quantitatively or stoichiometrically measure the concentration of hydrogen. So there's examples and just and instructions on this online. People can look it up. But the methylene blue method with platinum catalyst, not just any methylene blue, it's not going to work. It has to have the specific activator in order for it to work, and people can do that. Otherwise, for most people, I would just suggest that whatever product they're getting, that they are certified, like they have certified to IHSA criteria, the International Hygiene Standards Association. They have an H2 Analytics seal, for example. This way, it's been independent tested by reputable organizations that we know are using gas chromatography and measuring it correctly, and so on.
Okay, that's a good thing. And it says here, the next question is, since hydrogen is able to be carried by air or liquid, which absorbs the best into the cell?
Yeah, great question. So it turns out that it can absorb just fine, both of them, because when you take hydrogen gas, you dissolve it into water and then you
Right.
drink it. So the hydrogen gas is just dissolved in the water and then you drink it and then it's just diffused everywhere. In the same way you dissolve hydrogen gas into the water, that's the exact same thing that's happening when you inhale hydrogen gas. The gas is just dissolving inside of your blood in the same way it would have dissolved inside of the water. So it's almost the exact same thing. Now with inhalation, you do get hydrogen gas that goes everywhere. And so on the one hand, there's going to be benefits you get from inhalation that you don't get from water because hydrogen gas from inhalation goes everywhere versus
Right.
from water it doesn't. However,
Exactly.
water, from when it's dissolved into water, you also get other benefits you don't get from inhalation because the water is gonna has certain benefits like on the microbiome and the GI tract and the liver that you don't seem to get from inhalation.
No, yeah, I agree. I think doing both is, especially if you
Yeah,
have a very sick patient, I encourage them to do both. So,
yeah, I agree.
so since it's infused in water, how is it beneficial after it's exposed to the stomach acid?
Yeah, great question. And that's why we covered the different species of hydrogen. If we remember that pH has reference to the hydrogen ion in pH
Mhm.
versus the hydrogen molecule, a totally different species. And so it doesn't interact at all with the pH. It doesn't, you can dissolve hydrogen gas in extremely alkaline or a very acidic pH. There's no change, there's no difference because it's not an acid or a base. It's just a gas, it's a molecule. So you don't have to worry about that at all.
Okay. So someone asked, can you put the hydrogen in your eyes in a goggle format for macular degeneration? And yes, it's great topically. It's great for the
Yeah, yeah,
eyes. It's great. Yeah, it's fabulous, you know.
yeah, I think that's a new area, and there's some research already on hydrogen gas for ocular health. Now, when it comes to using like the goggles, I would say be very careful if you're using pure hydrogen or the oxyhydrogen because you're literally putting a bomb on your face. Because that gas becomes flammable and detonatable. And like I said, less energy than that is required to for static electricity is can ignite that hydrogen gas. So if you want to do that, using this Inhale H2 machine would be recommended because it's not flammable because it's below 4% and it's targeted. So you can say exactly 1, 2, or 3 or 4% hydrogen, and you can directly apply it to the eyes or other areas, and
Right.
you don't have to worry
You
about the
don't need
risk
the
of.
goggles. Yeah, right.
Yeah, or you could use the goggles, but you don't have to worry about the flammability. But
Mhm.
you don't want to use you don't want to use other methods because then it is flammable.
Yeah, and I tell people it's great. I use it for skin lesion, skin stuff all the time.
Yeah.
For any
Yeah.
kind of swelling, skin things, I mean, acne, everything. So people with post-surgery, people radiation burns. I've used hydrogen water lots. So,
Wonderful,
all
wonderful.
right. It says, do you gradually work up to a certain level, like start at 10 minutes and then add more, or how would you suggest?
In the clinical research, we don't tend to ever do that. We just start, like an hour, 40, 30 minutes, an hour, even, 3 hours. Some of the subjects, like with the post-cardiac arrest syndrome, they did it for 18 hours. That wasn't working up to anything. Hydrogen's very natural to the body, anyways. But so I would say if people are going to try, maybe try for at least 45 minutes to 30 minutes to an hour or so, and then yeah, maybe work up as you have more time or figure out how to use it. And see, you might be able to find a time where you're like, yeah, this is more optimal after maybe 3 hours. Or I think you even said that you have sometimes people's patients will sleep with it. So I think there's a lot of more research that needs to be done here, but you don't need to
Right.
worry about working up to it or something.
Right. You can do a full session, no problem. Right.
Yeah.
So can you sleep with the inhale H2? I'm sure you can, right?
Yeah, exactly. Yeah, you'd be able to figure it out. Yeah, I know Ben Greenfield, he did a thing or he slept with it and he's like, that's the best sleep I ever had. So
Yeah. So I've had
yeah.
lots of my patients sleep with it. So, and then
Yeah.
what about, do you think it would be beneficial for sleep apnea? I'm sure it's beneficial, right?
Yeah, yeah. There's actually some really interesting data on that because there's two things. One, to help reduce the side effects of sleep apnea that can happen, and that's one. And then maybe even helping improve sleep apnea in general. So there's two different things to look at.
So this is a little more complicated. It says, since your company is based on vapor hydrogen molecule, I'm assuming you think it's the best to get molecular hydrogen through the air. And it says, isn't water a better cure, or you can explain why not?
I think they're both great. It's kind of the same thing we talked about before. I think drinking hydrogen water is much more convenient, and I don't think there's a good excuse for anybody to not just be drinking hydrogen water because it's as long as we have the means to do it. So I wouldn't say one is necessarily better than the other unless you're targeting a specific thing. Like if you're targeting, say, the microbiome, then I would say probably hydrogen water would be better for that. But but maybe other situations, like maybe even for neurological conditions or something, then we could say maybe inhalation of hydrogen gas would be more effective, just because you're targeting the different organs or tissues differently.
Yeah, I think with people have specific like respiratory, I would recommend the
Yeah,
inhalation.
something like that. Yeah.
Yeah. And I tell people like also for the systemic, absorption, like I love them to do the hydrogen inhalation, but I have the patients do both, if you know what I'm saying. So
Hmm.
like I don't like I think most of my patients are doing both the hydrogen inhalation and it's very synergistic when we do chemotherapy. So
Yeah.
in
Yeah.
making chemo work.
I think so too. And there's clinical data on that. I think if people are going to use like chemotherapy or any just strong therapy, even like
Right.
hyperbaric oxygen or ozone or a lot of different therapies out there, they're just really strong, which is sometimes what is needed. Hydrogen is really a great tool to add along with that. And I would say, yeah, water as well as inhalation.
Hmm. So one of the questions is, does the product smell or taste metallic? But it doesn't have any taste. I,
Yeah, I mean, sometimes with the water, it depends on the product, right? So, sometimes we have different machines, and then like the pH increases, and that can give a different change. But hydrogen gas doesn't have any taste. Or there's the hydrogen producing
right.
tablets, and then of course that will have a taste because you have magnesium, you have organic acids, and so that can have a taste to it. But it's not the hydrogen gas. So yeah, hydrogen gas is an odorless, tasteless, explosive molecule.
Yeah. So yeah, because I drink it regularly. Now the tablets, like you said, do have when you dissolve them, they can have a taste in it.
Yeah, because it has a metallic magnesium, and then in order to get the magnesium to react, they add organic acids like
Right.
malic acid, which is in apples, and then of course that has a flavor, a taste to it. So, yeah,
Right. Well, this has been amazing. This is great. And it's so amazing that you've really exploded this in the United States with all the educational and the research. And so I know my patients, they're very evolved and smart. They do a lot of homework and due diligence. I appreciate you sharing your expertise and exploding this whole industry with hydrogen because I know in Japan how like I have people in Japan and doctors in Japan and how I've listened to many lectures about it and everything. So we need to bring
yeah.
these
Well,
life-saving treatments to the US. So,
well, thank you, and I appreciate you and your hospitality and for the opportunity to educate and for your education also. I mean, you've been talking to your patients and educating them and everybody else about hydrogen for a long time, and so yeah, I appreciate that and for helping to share this. Really, hydrogen is a passion of mine, just because. Again, hydrogen, we don't have a 10,000 human study proving
right.
that hydrogen is going to do all these things, right? Because there's no billion-dollar pharmaceutical company that's doing those types of studies. Most of the research we have is actually by government grants. And these are small, like $500,000, let's say, and that's good to do some studies, but not major clinical studies. And so my passion really comes from the fact that we know that hydrogen gas being a natural, safe molecule, and when you look at the preliminary evidence in animals and humans, it looks very promising. And so people should have an informed consent, basically, to say, yeah, I can either wait for the next 10, 20 years until we're able to have that evidence, if it really, assuming that it really does work right, till they have the evidence. But by then it could be too late. Or like what you're doing now, you inform your patients and give them tools and options, and then they can decide for themselves if they want to try that. And that's I just think that's important. And so when I do the research and look at things, yeah, I think yeah, this is something that I can economically afford. I want to at this point in my life try it for just overall wellness and health and things.
Right. Yeah, it's wonderful. I love it. So, well, thank you.
Yeah.
And thank you, everyone, everywhere that's tuning in today. And we do tape these. And so it will be available later on YouTube if you want to go back and watch it. And if you have any other questions, send them in. We always welcome questions, concerns, or comments about anything and everything. So thank you for being part of all of our journey today.